Hello, my name is Martin Ochoa. Today we'll be introducing my Phys142 Capstone project, inducing quantum anomalous Hall effects within graphene heterostructures. Now, condensed matter physicists are interested in 2D heterostructures consisting of graphene and other various materials, and the reason why graphene is an area of interest to us is because of its newfound, well, not necessarily newfound, but its highly interesting electron transportation properties, which consist of high resistance ambipolar field effects, and this ambipolar field effect implies a carrier switching, which we will get into in a moment. And the reason why we're also interested in graphene is because it has the potential to replace other electronic devices or electronic materials such as gold and platinum due to this high electron transportation. But one issue that has been found, well, it's always been an issue, that graphene does lack magnetic effects needed for these field effect transistors or quantum computation, and we aim to solve this by combining it with other materials in a Lego-like manner, as we can see in the bottom left. We can stack varying materials and pair them with graphene, and these materials each have their own unique properties, which will be combined and affected, or combine and interact with graphene, specifically the surface atomic lattice structure of the material. And this opens a whole new possibility of, honestly, I would say wonder, that it is extremely fascinating. So then, let's continue. Some of the materials we'll be interested in is a ferromagnetic insulator, as we saw in the previous slide. That will be our base, our substrate. Now, this one introduces proximity effect interactions, which we hope will induce which has been shown, honestly, to produce these proximity effects exchange. Now, not necessarily with this material, TiG, or thulium iron garnet, but with other ferromagnetic insulators. It has shown to slightly induce magneticism in graphene, which is highly, highly desirable, and truthfully, quite honestly amazing. Another material we hope to pair with graphene on the upper level of it, WSE2, or tungsten diselenide. This will help us create a spin orbit coupling effect within each atomic lattice structure. Now, what this entails is that this opens the possibility of opening a band gap within our devices and introducing spin polarization, which we will get into more detail in a little bit. But the spin splitting allows us to have two different energy values for the spin up and spin down of fermions, which are electrons. And this allows us to pretty much have more energy efficient devices, and, well, it introduces the idea of energy efficiency. But alongside that, it allows us to have two different measurements reading up and down. So we can kind of compute this to a 0 and a 1 in quantum computation, which opens a whole new avenue of how to use these electronic devices, or how to implement them in the far future for room temperature conditions. But as of now, all of these measurements must be taken in sub-zero, or not sub-zero, very, very low temperatures, like around the millikelvin range. On the right hand side, we see the desired effect we want. Now, this is the quantum Hall effect. What this entails is these steps are a value of, let's see, E squared over H bar and 4. Now, this is kind of important to us because it is quite literally fundamental units within our universe. E is the quantized charge of an electron. H bar describes the discrete values, energy values we find in quantum systems. And the 4 here signifies that since graphene has a honeycomb lattice structure, or hexagonal lattice structure, which I will draw here. Now, when we pair this with another material that has a hexagonal lattice structure, such as tungsten diselenide, some really interesting effects will pop up, such as called K-valley splitting and spin splitting. And these two values, since they're symmetric with one another, will add up and combine into a value of 4. And this is very unique to graphene in itself. Other materials have been found to have half this value, full integer values, half integer values, and for graphene, it is a constant for because mainly part due to the hexagonal structure and the shared lattice spaces between the other materials. And each step represents an increase of this value. So you can really think about us introducing a single electron into our system per step. And this opens a wonderful range of possibilities that are kind of akin to what I said previously about the spin splitting, where we have different energy values. We can finely tune our devices to really any degree of power efficiency at this point because we manually control how many electrons are introduced to the system. We can continue forward now. This will be the device fabrication roadmap. That is, these are the steps that are usually taken when producing one of these devices. We start off with exfoliation, dry transfer, pattern design, and then finally move on to testing. Now, what this entails is, what this first part entails exfoliation. We quite literally take Scotch tape and we grab a sample of graphene and or these other materials and we peel back one by one. And since the van der Waals forces between the multiple layers of graphene aren't necessarily as strong, we shear off a section of graphite. We shear off a section of graphite, which turns to graphene, monolayer graphene. The difference is graphite comes in bulk and graphene comes in little tiny layers. So we want these layers. And to me, I think it's amazing that we can take something as simple as Scotch tape, a commercially available product, and exfoliate a rock. Then we get this highly fascinating material, which exhibits properties unlike any other materials. I think that is one of the most cool parts I have ever witnessed in this laboratory. Now, on the right-hand side, we see exfoliated monolayer sample of graphene. Now, I want to be very specific in this that this is a single atom thick. So that means it is, if you want to think about it in a 3D representation, it's a sheet of paper. I think that is fantastic because this implies that whenever we combine it with the other substrates, TIG as the base and WS2 as top, we are sandwiching these single atoms, and they are being torn apart. Not necessarily torn, but they are being introduced to two varying different materials, and it's going to have a property effect on that one single lattice or that one single atom. Oh, let me see if I can visualize it here. So this will be the graphene, and this will be the other atom. The other atoms. So this is TIG, and this will be WSE2. Oh, I meant the 2 to go down there. Please ignore the top one. And this is graphene. So we can tell that this single atom is going to have an interaction with this one, this one, this one, while also having an interaction with these bottom ones, and so forth with these respectives. Now, this is very, very exciting, very crucial to our device per se, because without these, or without the single atomic layer existing between two different materials, these emergent properties will not arise. And again, as a quick reminder, the emergent properties of TIG would be proximity-induced magnetism, which is going to hopefully induce magnetization in graphene intrinsically, as opposed to having a strong external magnet being employed in the system, which is normally done to other 2D devices. And WSC2 is going to introduce the spin-orbit coupling of our material, and this is going to interplay to spin splitting and open up a topological gap. And I suppose over here, topological gap opening looks something like this, where we have holes up here and electrons. So we split this level right here such that an energy level can exist in between. and this opens up a whole new range of possibilities between our devices. Now, in order to actually build a device, we have to manually stack it. So as you can see here, this is a transfer stage. And zoomed up inside, it's kind of difficult to see. But right here exists the glass slide, and my sample lives on this sphere right here, or this cylinder right here. And on the left hand side, we can see a better representation of it. So with the glass slide, you pick up the subsequent material you want to work off. Oh, and I think I did forget to mention, we normally exfoliate on samples of silicon dioxide, SiO2, and this is done for practical reasons. I mean, silicon is it's expensive, but it allows us to see a better image of our materials once it's actually deposited on top. And then from there, we can extract them. And in order to extract them, we take a glass slide, a polymer called PDMS, and another polymer called PC. Now, the PC acts as tape, or as glue, I would say. So we pick up, we spot our required sample or desired sample on our silicon substrate after exfoliation, and we drop down our material, our picking up apparatus, which I will refer to as the glass slide PDMS PC configuration. So once the PC comes into contact with HBN, it would actually adhere to the surface. And since the PC has a stronger, I guess, force or adhesive force to it, it's actually going to pick up cleanly off of the SiO2. So now the HBN exists on the PC, and you can transfer it, you can move it around. It's quite literally like you take tape and you start picking up little samples of maybe an eraser shaving, and it'll just stick to the tape. And then from there on, you can transfer it on over to anything else. Now, what we do normally is we build a device one by one. So for this specific device, we have a TIG substrate, which is grown in a post laser deposition method. So that pretty much means we bombard a material up until it keeps blasting and forming this new material. And then we use that as a substrate. So we exfoliate it off of SiO2, and we place our TIG sample downwards. Then we pick up our graphene sample that we like, we place it on the TIG sample, transferring it. And then from there on, we replicate the process with WSC2 and HBN. HBN is going to be used as a top gate insulator, which helps protect our device from any external environmental factors. So once our device is kind of completed, we can see on the bottom left that it now resides on a TIG substrate, graphene is present, and WSC2 lies firmly on top. Now, this region that is boxed in right below here, or crossed in, better yet said, that is the region where all our interaction is going to happen. And the quantum anomalous Hall effect, the chiraless transportation of the electrons, is going to form around that edge barrier we see there, the corner pieces. Now, we top it off with the HBN to secure our device. A method before we actually finish building a device is we create a Hall bar. And this Hall bar allows us the ability to take these quantum transportation measurements. Really, the resistivity measurements, we apply an external gate voltage, let's say right here, and another one right here, such that current is going to flow from one end to the other. And these other devices, these pads, are going to help us read our resistance, either resistance going upwards or resistance going across, as we can see here on the bottom right schematic. Now, XX stands for longitudinal resistance, and XY is the interesting one. Well, they're both interesting in their very own right, but XY is the Hall resistance, and this tells us many more properties of carrier mobility and so forth. We will get into a bigger discussion in a little bit. On the left-hand side, we can see a little bit more of a schematic where we can actually build our hall bar, or design our hall bar, better yet said. These are alignment marks, which are nanometers in scale, or nanometers in scale, and it allows us to pretty much orient ourselves on our device, such that when we move on to the next process, everything will be a little bit more easier for us. Now, in order to actually write our patterns and etch away at our sample, we do electron beam lithography. Now, this is the process of bombarding our material with electrons. And in the process of doing this, we create little holes in our device. And that has etched away at our sample, creating the hall bar we saw previously. Another method to do this is, instead of applying a material that is light reactive, which allows us to bombard it and move away at it like sand does, we do something that is light resistance. So once the light touches it, it will not affect it. And every other surrounding region that does not have this material applied to it will be disappeared, or will not be adhesive to the sputtering process. And the sputtering process really entails us spitting materials such as gold or platinum onto a device, so that these vacancies, these holes, are filled up with our desired material. And we do gold and platinum just because they're one of the best materials to actually do conductivity measurements or resistance measurements, because as of now we use gold and platinum and silver and other materials like that for electron transportation measurements, just because they're really good conductors. And so that's the idea here. We want to replicate that idea, but also recall that graphene is a fantastic conductor. So when this interaction comes to the graphene, we hope that the electrons entering the graphene barrier go as Dirac fermions, and this pretty much entails that they're massless relativistic particles, which opens up a whole new possibility of wonder. And this is why graphene has been found to be an electron transportation like super material. And I'm not the one saying super material out of my own words, but these are like replicated in papers that the first people who found it have called it a wonder material, which I think is really fantastic, considering that it's just graphene. Now, our final device, as a recap, we have our TIC substrate, we have our graphene. We then etch our device, as shown in the bottom left, and sputter the material on top. So now we have a hall bar resting on top of graphene. We then apply our WSE2 to get the spin orbit coupling effects, and top it off with HBN. Now, this graphite you see on top, since graphite is a pretty good conductor already, we use it to exploit it. We pretty much create a capacitor-like reading, and we're able to, I guess, take more measurements than we normally would, as we're not locking ourselves out of the system. Now, earlier I had mentioned that we were talking about carrier mobility, and carrier mobility is what links like energy flow to higher, more efficient devices. Now, energy flow, such as carrier transportation or electron transportation in this case, the higher it is, the more heat resistant it is, or the less heat it generates. Because you can imagine that in a little corridor, if the electrons are speeding fast enough, they're not going to hit anything else. But if they're relatively slow, they're going to be bombarding on the walls and creating heat. Energy is going to dissipate off of them. Now we have the drift velocity, conductivity, and Ohm's law. Now, conductivity is the inverse value of resistance. And truthfully, easy method I employ myself, that if it has high resistivity at one point, that means it's going to have low conductance at that exact same point. So we want to move away from that high resistivity point. That is what is crucial to save on energy. And in graphene, showing this ambipolar field effect, which I said I was going to talk about later, I'll mention it right now. Now, this ambipolar field effect is pretty much the switching of carrier types. And we will see in a graph shortly that the carrier type is actually corresponding to which side of the resistance graph and which side of the conductivity graph you reside in. So there's holes, positive electrons, and then electrons, the basic ones being negatively charged ones. And as you can see here by Ohm's law, it's just that, higher conductivity materials will have a large current density. So that means we're out there pushing electrons at rapid speed. And on the bottom right, we can see, this is why graphene is a fantastic electric conductor. 3,000 to 10,000 centimeters velocity or voltage a second. Now, that is extremely, extremely fascinating. Look at it compared to gold and copper, the next best materials used in room temperature electronics. It is a substantial difference. Now, here's the relation between conductivity and mobility, which I was hinting about earlier. Now, it is just the inverse. So if you have resistivity, the more carrier mobilities, or if you have conductivity, the more carrier mobility will be reached at, or the more conductivity will be reached at higher carrier mobility. And again, carrier mobility is just how many electrons or holes are passing through our system at any given time. You can equate this to how fast water is flowing. And conductivity is how wide the gap is. That's one way I like to think about it as well. Now, Now we reach the experimental techniques. This is how we get our device values, our resistance measurements, our field effects, our Hall effects, our Hall effect measurements, and our field effect measurements. Now, a little bit more on the ambipolar effects. So, earlier I had mentioned a Dirac point, a Dirac voltage. Corresponding to this graph, our Dirac voltage, VD, is around this point, 18 millivolts. Now, this pretty much signifies that at this peak resistivity graph, we have absolutely no carrier mobility. That means the hallway, if this was a hallway, this would be a narrow passage where electrons have to squeeze in one by one. But as we move away from it, we get a bigger passage, allowing more electrons to squeeze on by. And this happens on both cases. Well, with a little bit of caveat. Right here, electrons are moving backwards. Right here, electrons are moving forward. Now, on the right-hand side, we can see a conductivity graph. Take note of where minimum conductivity is at. This is also where the Dirac voltage is at. Now, this correlates to exactly the same thing, a narrow passage where no electrons can get through. But as we move further away from this measurement, our hallway starts to extend up until we get to a point of maximum extension, where now we have many, remember, holes in this case on the left-hand side. These are, it says negative, but it's a little caveat that holes are positive. But now we have maximum carrier mobility, which means maximum energy efficiency, leading to less heat transportation and all these other effects. Now, and then this is also fascinating for graphene, is because we can choose what carrier type we would want to use. And this is pretty much akin to what I was saying earlier, a 0 or a 1. We can tell the system that, hey, we only want you to activate when you have negative voltage or when you have positive voltage. And at this amount of energy efficiency, or this amount of carrier transportation density, which is key, which is absolutely necessary for the quantum anomalous Hall effect to appear, and efficient for these new age electronic devices. Now, the Hall effect in graphene. Earlier I had mentioned that, or this is the Hall resistance already had said. We apply an external magnetic field on our device and the Hall effect occurs. Now, normally when you have a little device, electrons just go up or down. But if you have a external magnetic field, B field as we call them, a force acts in our speed, against our electrons. So if our B field points up, our electrons are going right, a force will be acted upon them, and it wants to push these to the side. So instead of our electrons just going in a straight line across our sample, we now see this really cool effect where they're pushed off to the side and they want to live on the edge. Yeah, live on the edge. So we take other little varying devices or magnetic fields up to 1 Tesla and 14 Tesla. And 1 Tesla is around 1,000 or 1 to the fourth. 1,000 to the fourth Gausses. And a fridge magnet, I want to say, is around a fraction of that. So truthfully, you don't want to be next to one of these if you have a pacemaker. And on this graph here, we can analyze that again at our Dirac point. Now, this Dirac point is very, very key as you have found evident. At this point, we have an equal amount. This is what graphene's conductance band looks like, 2 triangles. Now, at the Dirac point, we have an equal amount of holes and electrons. Now, this pretty much negates our carrier density or carrier concentration, and we can think about it as a dam, a pool of water that has been filled to the top, and really nothing else is going to happen to it. But let's say we spill the dam, so then electrons want to flow outwards. This is the electrons. These are holes which are positively charged. If we open the dam and the electrons spill out, this is pretty much us switching our type. And this is opening the dam, so if they spill outwards. But let's say if someone punches a hole on the bottom of it, or better yet, makes a sink down here, it flows back down for the positively charged ones, I suppose. But yes, another key takeaway from this one is the further away we move from the Dirac voltage, the better our carrier concentration gets, the higher our conductivity gets, the more energy efficiency we have, and the less heat formation we get. Now, one phenomenon that is essential for the quantum anomalous Hall effect to occur is that these subnikosta oscillations must be present in our conductivity graph. So, this is magneto resistance. My apologies. This should be conductance in the longitudinal axis. So our x-axis should be 1 over, as we said before. So what these oscillations tell us is that at every one of these points, a new electron or hole is being introduced to our system. This is akin to, I guess, if you want to think about, if you're at a pond or a fountain and you want to make a wish, you throw a quarter in the system, or you throw a quarter into the water. You throwing this quarter into the water signifies you added an extra electron to our system, increasing the energy efficiency, or if some cases, taking away from the energy efficiency because you have restricted the electron from entering. Now, these oscillations signify a spin, uh, well, a beat frequency, and the spin signifies a spin splitting has occurred within our values. And if you recall from earlier, the spin splitting determines different energy levels. So we gonna have different. You have a spin value for up, or an energy level for up, but these ones will no longer be equal to one another, allowing us the opportunity to exploit them for, I guess, for spintronic applications. Spintronic applications are fantastic. This is possibly the best way for quantum computation. And alongside this is proven that a band gap has opened within our device. And if you recall before, this is what the graphene band looks like, where we look like that. Now, it has the potential to split, creating this region of forbidden electrons. And this is really where all the physics and all the magic happens. Because once the spin splitting has occurred, quantum phenomena will occur. This is pretty much saying that our electrons are confined to one area. Now they will jump, or they will be discrete or quantized to the next one, meaning they cannot exist in the middle, and they know they cannot exist in the middle. So then they either go up or down in energy level. And this is what's really crucial for our future of electronic quantum devices. On the right hand side, we see another image from a paper which beautifully accepts or beautifully demonstrates the Hall effect with these diminishing qualities and the spin splitting. Sorry, excuse me. We can see that at this value, it has a different energy from this one right here, meaning we have shifted left and right, giving us a unique value for spin up and spin down values. And thank you. This was my talk, or my capstone presentation. As you can tell, graphene is a phenomena system that has many, many different occurrences or many different possibilities to be exploited. And I do highly suggest taking a look at, if you want, this paper. This paper is phenomenal. It is a bit dense, I will not lie, but this is what started the entirety of graphene systems, or graphene wonder in many physicists, and ultimately the far off goal of getting quantum anomalous Hall effect to be occurred within graphene systems. And if you continue reading my paper, I go into a little bit more detail as to what these applications are, why we want them, and truthfully why it can be a very, very useful material for the future generation of not only physicists but everyday people who can have reduced energy cost, faster electronic devices, quantum computation, and then ultimately the far off goal is obtaining all of this quantum effects within room temperature environments. Because as of now, most quantum effects only occur in not sub-zero, I keep saying sub-zero, or in millikelvin ranges where discrete values are allowed, and discreteness and the fuzziness of electrical heat transportation doesn't get in the way of energy measurements. And then this is a little bit more supplements on the energy bands and energy carriers, where I kind of draw a little bit better of what this kind of represents. And we can see here the Hall resistance and the regular longitudinal resistance, or magnetoresistance, better yet said, I suppose. But yes, notice at VD we have, oh, I missed it. But we have this zone, this forbidden zone, where we have equal amounts of holes and equal amounts of electrons. Thank you. And I do hope that this has sparked an interest in graphene or 2D electronic devices just as it has for me. This is a really fascinating topic to be a part of. Thank you.